Sweet. Yes. I'm Joshua. I work at Uniswap Labs on Unichain. Today, I'll be talking a bit about Unichain, a lot about the OP stack, and some of the extensions we've made on it, and kind of how it all fits together. Yep. So this is what we're going through. First, the OP stack, then Rollup Boost, which is an out-of-protocol extension to the OP stack that's built around interesting things we can do with block building. Still probably less interesting than what Flash Bots has done on layer 1, but we're starting to evolve layer 2s and rollups. Then I'll talk about Flash Blocks, which is a very exciting extension to rollups. And then lastly, just a blurb on Unichain. Cool, the OP stack. What is the OP stack? It's an open source suite of software which implements an Ethereum virtual machine rollup. So I'll start with what the EVM is. It's just a virtual machine. So you write some code, it compiles down to this specific language. Kind of the key thing with the EVM is we've heard about Solana, we've heard about some other L1s. Any protocol like Uniswap, which is built for the EVM, can easily be moved to different EVM chains. So EVM chains kind of form their own ecosystem versus something like the Solana virtual machine. You can't natively take the Uniswap contracts and put them on Solana. You'd have to rewrite them and go integrate directly. So that's kind of OP Stack, very focused on this EVM ecosystem. Then it's a rollup. A rollup is a blockchain that uses another blockchain for data availability and ordering. I'm not going to beat this dead horse, but it's just a blockchain is kind of the key aspect to it. Okay, going through the OP stack, kind of one way to think about it is these high-level components. We have sequencing and block building, which is how a transaction comes from a user and gets included in a block. Probably where we'll spend the majority of the talk today. It's the most interesting part. There's batching, which is how a block gets submitted down to L1. The mechanics of this, very engineering heavy, and there's also some fun fee mechanics that will be talked about later. Then lastly, we have proposals and withdrawals. So this is where a user burns their funds on layer 2 and wants to withdraw them on layer 1. Okay. Here's all the pieces of software which implement this. This is my day-to-day, maybe not yours, but OP-Node is a consensus layer client, OP-Geth, OP-Reth, execution layer clients, Rollup Boost is a fun proxy in the middle, Batcher does batching, Proposer does proposing, Challenger makes sure no one's stealing the funds. Cool. And then here is this in a system diagram view. We can see our user sends a transaction to the sequencer. Sequencer sequences it, includes it, and then pushes out a block with that transaction to the rest of the network. At the same time, the batcher reads this block, pushes it down to L1. Then once the block is on L1, everyone reads this block. And then lastly, the proposer pushes a state root back down to L1. Okay. Also, I didn't say this at the start. If you have questions, feel free to interrupt me. I'll try and explain that as best I can. Okay. So on to sequencing. So this is OP Stack, in essentially every rollup ever has a single centralized sequencer. So this is for the OP Stack, a sequencer is both the block builder and the proposer. So when you think about Ethereum, there's a million different validators. That's the proposer. So out of a million people, someone can propose the block. And then you have those 3-4 major builders who are responsible for building the block. On the OP Stack, there's one. It's basically true for every other rollup. And rollups use the way they're designed to enforce guarantees on the system. So the sequencer obviously has a lot of power with how it can order transactions, but it's not an infinite power. It cannot fake transactions. That's validated. Nodes will reject any block which has that. And then many rollups have a forced inclusion mechanism which allows a user to bypass the sequencer in case the sequencer is censoring their transactions. Yes.
Do you assure no fake transactions? Can't I, like, if I run a sequencer, can I just create a transaction as an individual LMS?
Yep.
Yeah. Or address?
Uh,
your money.
yeah.
Oh, I see, okay.
Yeah. So yeah, as a sequencer, you can insert a transaction wherever you want if it's your own funds, but you can't steal user funds.
Can you say something about block size is very tiny, so there's less space for data.
Yes. I guess kind of by default, the OP stack is 2 seconds per block. Unichain's at 1 second per block. Flash blocks takes that even lower. So what it looks like from a user perspective and like an LP perspective is very, very fast blocks. Answer your question?
I'm just saying that it's not like L1, but there is more transactions, so there's more space to MEV.
That depends on the chain. Base is doing 10x the TPS of Ethereum mainnet. Okay.
So this is sort of like Anna's question, but a different way. So front running by the sequencer. Like that there, yeah, it is my funds, but
Yes. Well, I'll talk later about some of the work we've been doing on Unichain to constrain the sequencer from front running. But default OP stack, it is possible to front run on the sequencer.
And is it as optimistic?
Uh, Oh, that's a great question. So OP stack is an optimistic rollup. That's what OP stands for. It stands for optimism. In a year from now, I would not bet on the OP stack being an optimistic rollup or being only an optimistic rollup. I'm not going to. I don't have slides on this, but we are very focused on how do we turn this into a ZK proof for withdrawals. So in a year from now, OP is just going to be like a trademark, I guess. It's going to not mean anything, but I don't think we're rebranding, but maybe it could be the ZK stack.
I have a follow-up then. Because so like a bunch of different L2s rollups use the OP stack, right? So like when you say we will not be or may not be an optimistic rollup, like are you speaking for Unichain, for like optimism, for
I can influence Unichain the most, but I think it's broad for chain operators on the OP stack, where I think we're all pretty broadly interested in ZK proofs because they have a lot of advantages specifically on the withdrawal speed.
you think the 1 year horizon, like that's like you said 1 year, that's actually also kind of an interesting thing. Like, is there something coming down the pipeline here?
This is just based on like where I see the tech. Like there are chains that are smaller that have done ZK proofs of the OP stack and are kind of like running them on small chains. The most confident thing I can say in like a year, there will be an OP stack chain which is running ZK proofs on the side. I don't know if it'll be the only proof system, but yeah. So optimistic for the moment, but heavily invested in going to ZK.
So, but taking a step back and maybe also considering all the other questions that we have here, what can a sequencer do? Can you front run and so on and so forth? Fundamentally, I think what we can think about this is very close to just a system sitting on top of a blockchain with a certain set of constraints. And so there are some that are given by the system itself, like no fake transaction, force inclusion mechanism. But you could also imagine that you have additional constraints that are voluntary, right? So you can run an exchange, sort of, has say time priority over that, right? So there's different models that you can have for a rollup.
Yes, absolutely. I'm gonna get at this a bit more, but like, yeah, these in protocol constraints around like faking transactions are something we can enforce with fault proof. There's out of protocol constraints, which I'll talk about how we do that with trusted execution environments. And then there's always the last constraint of reputation. Just trust me, bro. But as a chain operator, like we do have a brand. We do care about fair ordering. Unichain is not sandwiching and front running your transactions. Okay, so a lot of these constraints are actually going to be on the block building process. So I'm going to dive in a bit more about how we do that. So here's the vanilla OP stack block building. We're going to extend this diagram a bunch, but basically the sequencer asks the execution client, hey, start building me a block. Execution client says, here's my payload ID. It's kind of like taking a sandwich number at the counter. And then the sequencer waits until the block time, hands this ID back and gets the built block. And then lastly, they publish it out to the network. There's a separation of responsibility between like, this is our proposer. That's the one that signs off on the block, but that's the one that actually builds it. This is a side thing, little bit to set up later talks, but fees, it's kind of like Ethereum with 1559. And then there's an L1 data fee, where right now, you look at a transaction, you estimate how large it's going to be, and then you look at what the current Ethereum blob fee market's doing, and then you charge an amount which is supposed to cover the cost of batching. There's a lot of asterisks on covers because the fee is taken, or you charge a user at a different time from your cost is incurred, and then there's some flexibility in how much of that cost you cover.
What happens with the base fee? Is it collected by Unichain or?
Astute observation. For the OP stack, this is the one difference between OP stack and Ethereum is the base fee is collected, unlike Ethereum where it's burnt.
So like, is it pure profit? Because in Ethereum, the reason why you collect fees is to compensate for the cost of staking and so on. But what's the cost here that is being covered? Or is it just pure profit?
Base fee. The base fee is a congestion mechanism. Same with priority fee a bit. Yes, it's mostly profit. There are real costs to operating a chain. The sequencer nodes are very large machines. They're not cheap to run. But both. But like you do need some sort of mechanism for deciding how do we allocate the scarce resource of block space, and these auction mechanisms work really well at that.
Is it blocks full?
Unichain, not consistently. Other chains, very much so. And then Ethereum's very, very full.
Is like base fee, priority fee revenue enough to cover the costs of operating a sequencer, like in practice, like on Unichain or?
Yes. This varies by chain. For Unichain, which is kind of interesting, the priority fees are substantially larger than the base fee revenues. That may not always be true, but that's true at the moment. Cool. Now we get to, this is nominally proposals and withdrawals, but this is really about when a sequencer creates a block, it has some transactions, it updates the world state, and we have to reflect that world state back on L1. Most commonly for a user says, I burnt my money on L2 and I want to withdraw it on L1. And so anything which directly impacts the calculation of that state root from the data submitted is kind of in protocol, something we can validate with this fault proof system. And then as we talked about, block building is out of protocol. We mentioned that a bit earlier in the MEV boost design and extended block building, where it's not mathematical formulation where every node has to do it the same way, but it then creates a block, which then is inside the protocol. Here's a couple more examples on stuff that's in protocol, like signing off on your transaction, making sure an Ethereum balance is never negative. And then out of protocol, mainly on the block building side. As an example, that's something I don't think you could ever run a fault proof over or put fully in protocol is first come, first serve transaction ordering, because you just have to put all of the transactions on Ethereum to be able to do that. Another example is priority ordering inside a block. You could kind of put that the output has been priority ordered inside your fault proof, but you couldn't put that an anti-censorship property on dropping a priority ordered transaction inside your fault proof. Back to the block building side. Yeah, here's our table.
Is the mempool for the for Unichain public?
Most OP stack, I would essentially say all OP stack mempools are private. A lot of I think Arbitrum is as well, most L2s, because there's a single centralized entity that does block building, doesn't need to publish transactions.
Help with being first in, first out and censorship.
Yes, if you can figure out how to put that proof on chain, you can kind of do it with trusted execution environments. It's very hard to prove that something didn't happen, so it's hard to prove that you didn't drop a transaction.
They go into the trusted execution environment, and then you can only pick it up from there.
Yes, now that gives you that. Now you have to move the TE proof on chain, which is a solid proof, and that's something we're working on and like have built up a system to do. Other questions? Cool. Yeah, so in protocol, fault proofs, incredibly strong guarantees. So we discussed it's not always possible. And even when it's possible, it can be harder to implement. And if you decide to put something in your block rules or block validation rules, that logic has to live forever. Even if you deactivate the feature, it's got to stick around because you have to know what the rules were to validate historical blocks. And then we have our out of protocol rules, which are a lot quicker to implement. We can be a lot more flexible with experimenting with different block building policy. And then we have less good confidence compared to fault proof. That's not no confidence. A trusted execution environment can get you some confidence that, for example, we're doing priority ordering or other constraints. Cool. That's kind of high level view of the OP stack. Now I'll talk about rollup boost, which is where we do a lot of these TE building and TE constraints. So now rollup boost stands for a lot of things, but one of them is it's a proxy between our sequencer and our remote builder, which for Unichain is OPR builder running in a trusted execution and client in a trusted execution environment. So anytime the sequencer asks for a block, it asks a local OPGAF node, and it also asks this remote builder. And then often the remote builder is the one actually building the block, and then it'll sign off to say, I was a block built in a trusted execution environment. We've talked a lot about why we're doing this. I think the cool thing is like, oh, go ahead.
Is there an option between these two? The roll-up boost, does it decide based on who bids more and something like that?
No. So you could, but for the moment, we're not doing that. And for Unichain, I don't think we will. It basically always chooses the remote builder if the remote builder responds with a block that's not empty. Yeah. Yeah, and so this gives us a way of, in the future, you could do auctions, could do other interesting things. Mainly, we're interested in how do we actually enforce a fair ordering, and so we're not always interested in the most profitable block for us if that leads to negative externalities to our users.
It's failed. The ordering is first come, first served.
For us, it's no priority ordering over first come, first serve. There's some interesting things around Uniswap X and some of our auction mechanisms where priority ordering is interesting and helpful.
Could this theoretically be run faster than the Ethereum blockchain?
Yes, I have a whole section on that. Yeah, let's see. Quintus talked earlier about how you actually go through and prove your code and properties. So I'm not going to try and explain it with words when he had nice diagrams, but for Unichain, Flashbots is a partner and it's running OPR Builder with us, and it's been very involved in the development of this technology. Cool. This also gives us bundles. Enables revert protection. We can have users target specific blocks, even specific flash blocks. It's a fun property. This is my only attempt at economics in this entire talk. I got a lot of questions last time about denial of service or like spam attacks on revert protection, where basically if you send a revert protected transaction, you don't pay a fee if it reverts. I will argue that the fee is 0, but the cost to the sender is not 0. And then on our side, we can change how much it costs us to screen it. So we can change this balance. So I feel like economics people think of like fees and costs as fixed, or like kind of like that. You like have some system, you look at the equilibrium, but as an engineer, I can perturb that equilibrium in my favor. Cool. That's rollup boost. Sweet. Flash blocks. How do we go even faster? Favorite diagram again. So now rollup boost, same thing, asks.
What are we going right now?
200 milliseconds. Or also. So the rollup boost asks those builders for a block, and the remote builder every 200 milliseconds will push back a flash block to rollup boost. Then rollup boost pushes that out to a proxy. And then as a consumer of flash blocks, you can subscribe to the flash blocks that are coming out every 200 milliseconds. And then at the very end of the second for Unichain, it'll push back the full block, and then OP node sees that full block. So kind of from the protocol perspective, yeah, there's a block every second. From an end user perspective, there's a block every 200 milliseconds.
What's the use of the flash blocks?
And what's the difference?
I'll start with the use. If you have the final ordering of your transaction after that 200 milliseconds, the price at which your trade executed is finalized. So basically, it allows you to get your swap confirmation with the final execution price in 200 milliseconds rather than in a second.
Why wouldn't we get the final block?
I'll go over a bit why we prefer flash blocks to blocks, but yes, they're nicer than full blocks every 200 milliseconds.
No, yeah, I was wondering what the difference is between a flash block and a regular block.
Yes. So here we go. Here's a full block. It's got a parent hash. It's got a state root. So parent hash, it knows at the start, these state roots, transaction root, receipt roots, those are, you can only compute those after the end of the block. And they're actually particularly expensive to compute. The state root especially is offensive to compute. And then it has all of the transactions, say 0 to 100. But as we have our flash blocks coming out, we kind of still know our parent block, but flash block 0 has this ordered list of transactions 0 to 10. And then the next flash block number 1 has 11 to 25, and it has to extend these transactions. And then finally, we have 26 to 40. I guess we'd have another 2. And then only once we have 5 flash blocks do we seal the block, calculate the state root, calculate the transaction root, calculate all the information after. And part of the reason this works is that transactions in Ethereum are deterministic given a starting state. So if you have the exact same transactions, you'll get to the same state. So we don't need any of this information to kind of know what the state will be. We just need our starting state and the exact same list of transactions.
transactions are already confirmed in the sense that we know that there are no conflicting transactions.
Yes, there will be no conflicting transactions, and we know the final execution of the transaction after it's done, once we have a flash block. This kind of assumes that you don't decide to push out a different flash block or like finalize a different block, but once we push out those flash blocks, we put in work to make sure that will be the final block.
In the flashback, we have the application, so it's kind of like.
We do execution on the flash block. We just don't do state root computation. Execution's faster than state root.
So how do you know that there are no conflicting transactions? Are you trusting the user to give you like the list of all that you are checking?
We check it. So when we create those flash blocks, it's kind of like running a block building process every 200 milliseconds. So we have a list of transactions which are considered for inclusion. We pull them by priority fee. We execute them. We check the validity. And also in Ethereum, you can, unless it's a conditional bundle transaction, you can check validity relatively cheaply before execution. Ethereum says if you have a transaction which like reverts or has invalid opcodes or otherwise fails at the execution state, we're just going to take your gas. So it's basically designed to handle people spamming transactions and like handle like, okay, we got to the execution step. You incurred a cost on the network, you're going to pay that cost.
Is there a chance that block never actually gets completed even after like the first flash block was confirmed?
Yes, but that's where the engineering work goes to make it in practice, no.
Is that the risk user is taking by treating the flash block confirmation as being as good as the actual block inclusion?
Yes. There's a whole also hierarchy of like unsafe versus safe versus finalized that I don't really have time to talk about today in the OP stack. But if you, the long answer is if you're an exchange, even this final block, you probably wouldn't trust as finalized.
So when can a block fail when you start it on flash blocks?
Gosh. If L1 reorgs enough, if the sequencer decides to equivocate, there's a couple cases that could result in it. Oh yeah, here's the words version. It also has some metadata. Not strictly necessary, but it's nice for consumers. Yeah, 200 millisecond conversation. And here's also why we want to do them instead of full blocks, because the overhead is substantially less. State root is sublinear in the block size, so the larger we batch it up, the cheaper it is on like a per operation cost or a per transaction cost. Block headers also, they're cheap, but they're not free. And so if you think about 5xing or 10xing the amount of disk space you have to spend on block headers, not a huge number, but it's something that I think about in terms of the sustainability of a chain. Cool. Those are flash blocks. They're very exciting. Rolled out on Unichain, they're rolled out on Base, probably coming to more networks soon. And they're also, I guess, the last comment is they're kind of out of protocol, which is very nice for being able to experiment with them and develop them. In the future, I'd like to bring them in protocol, but that requires a lot more work, which is why we develop them out of protocol first and validate that people like them. Cool. Unichain. Finally get to what we do. This is, I guess I have to have a slide on this, but that's kind of when I work on Unichain, when we work on Unichain and Uniswap Labs, this is what we think about, making it the best place for swapping and decentralized finance. So that's a particular focus for us. And on the OP stack, it's a very strong EVM base. There's a lot of scaling work being done in the broader ecosystem. Annika will talk a bit more about that after me. And then some of the extensions we've rolled out around priority ordering and rollup boost and having users trust that they're not going to have their transaction sandwich are nice. The flash blocks, people really like the faster trades. Also, looking at lever with LPs, the faster you can arbitrage, the better it is for the LPs, and we need that side of the marketplace as well. Got some future stuff going up, but yeah, that's what I've got. Questions?
The limit, the 200 millisecond flash bonds, is that somehow a firm limit? Could you make this 2 milliseconds? No, so there's a reason to ask, right? Because
Oh.
think of traditional markets, they're now operating at microsecond speeds,
Yep.
right? So the question is, can you approach continuous trading?
Yeah.
What's a
Well, so
good
uh,
ask?
there was a funny thing where initially it was like 250 millisecond flash blocks, and then somehow they became 200 because there was a lot of desire among people on Twitter to say our chain's faster. But so in terms of getting down to like a microsecond, I think at that point, you're no longer thinking in a model of we have a batch of transactions. We're going to order transactions based on their priority fee, which basically running an auction for Uniswap X, like kind of in the background there, and you're just like taking transactions first come, first serve, which has some benefits, but I don't think we're going to get there. And then the latency on pushing out those transactions starts to get tricky. And like for a UX perspective with humans, once you get down to 100 to 200 milliseconds, people don't notice. Machines notice, but I think we're fine with that.
Can ask, like, impacts the decentralization piece, because then if you're like on the other side of the world, then you're disadvantaged.
Yes, that's a good point. The round trip latency to send a network packet from like here to the other side of the world is like 150 to 200 milliseconds. And that's just a firm constraint based on the speed of light. So if you want to go microseconds, you're talking about machines that are physically in the same room, networked closely to each other.
You talk about interrupt.
Sure. There's a lot of excitement about it. Optimism is working on it still.
So, okay, so now I mean, a lot of what you do is obviously predicated on the usage of Uniswap in your app, but fundamentally decentralized finance is everything. And when you have it on a roll up, you need to get the funds there, right? You need to get the liquidity. So do you foresee that there could be any problems with this? And this is actually a genuine question, because there's a question of there's lending protocols. You need to get the users to contribute the funds. And so, there could be some tension also with the L1 at some point and the users of it. So what's your view there? Because kind of what DeFi is really all about, right? It's not about, I can trade somewhere on Uniswap, right?
Yeah, no, that is something we're thinking about over the next years. Like swapping's great, but having lending markets is beneficial. There's more than just swapping is the DeFi ecosystem. So for Unichain, Uniswap's very good at swapping and trading, but we're also looking at that broader ecosystem.